Hello everyone, so we are back again with a new topic, that is design for simple stress part B. Okay, so moving on to the next point, next slide, that is the torsional shear stress. Okay, so here in this diagram you can see shaft subjected to torque. Here this figure you can see the shaft that is subjected to torque here, and this figure number B you can see torsional shear stress distribution. Okay, so figure A shows a shaft subjected to torque. Okay, so stress induced in a machine member to resist the action of twist is called torsional shear stress. It is given by tau is equal to TR divided by J. Okay, so where T is applied torque, R is radial distance of the fiber from the axis of rotation, and J is polar moment of inertia of the shaft about the axis of rotation. Okay, so distribution of torsional shear stress is shown in figure B. So stress is maximum at the outer fiber and zero at the axis of rotation. Okay, so angle of twist for a given value of applied torque T and length of shaft L can be calculated using this relation, that is T by J is equal to G theta divided by L. Okay, where theta is what is the angle of twist, which is measured in radians, and G is modulus of elasticity. Moving on to the next one, that is the bearing or crushing stress. Okay, so first of all we should know what is crushing. Okay, so crushing means to press or squeeze with a force that destroys or deforms, or to squeeze into small fragments. Okay, crushing or bearing stress is defined as the compressive stress developed at the surface of contact between two interacting members that are relatively at rest. Okay, so crushing stress is assumed to act uniformly on the projected area. Here in this figure you can see the crushing stress in riveted joint. Okay, and here in this figure you can see the bearing pressure in journal. Okay, so this is the fixed journal, this is the rotating journal. It's having diameter D and length small l. Okay, okay, so consider a riveted joint as shown in figure. So if D is considered to be the diameter of the rivet and T is as the thickness of the plate, crushing stress is given by this equation, that is sigma crushing is equal to load by projected area, which is equal to P by dt, which is less than and equal to sigma C. Okay, so if N is the total number of rivets used, okay, then total projected area will become N into D into T. Okay, so also the local compression that exists at the surface of contact between two members that are in relative motion is called bearing pressure. Okay, for example, bearing pressure exists between the contact surfaces of a journal rotating in a fixed bearing as shown in figure. So for a journal of diameter D and contact length L, bearing pressure is given by P bearing is equal to load divided by projected area, which is equal to P divided by D into L. Next, number 6 is the thermal stresses. Okay, materials expand with increase in temperature and contract with decrease in the temperature. Stresses develop in a component if it is prevented from freely expanding or contracting under the effect of temperature change. These stresses are called thermal stresses. Okay, so change in length of any machine member as a result of temperature is given by delta L is equal to L into alpha into T. Okay, so where L is original length of the member, alpha is coefficient of thermal expansion, and T is rise or fall of temperature. Okay, so if this change in length is prevented, that is the member is not allowed to freely expand or contract, strain induced in the body is given by this equation, that is thermal strength epsilon Th is equal to delta L by L is equal to L alpha T divided by L, which is equal to alpha T, and thermal stress sigma Th is equal to epsilon Th into E, which is equal to alpha into T into E, which is less than equal to sigma. So here where E is modulus of velocity of material of the member. Okay. Next, combined loading and principal stresses. So when a machine component is subjected to only axial load, bending moment or torque, uniaxial state of stress is produced, which was discussed in the previous lesson. Okay, but in actual practice, the components are mostly subjected to combination of loads. Example, transmission shaft is subjected to bending and torsion at the same time. Combined loading leads to complex state of stress. Infinite number of stress vectors act at any point inside the member subjected to combined loads, as infinite number of planes can pass through a point. Each stress vector is characterized by the corresponding plane on which it is acting. State of stress at a point is the totality of all stress vectors acting on it. For design purpose, it is very important to know the state of stress so as to determine the critical planes, the respective critical stresses, and relate them to the strength of the material. So with this, we have concluded the lecture on this topic. Thank you everyone.